Good morning. Welcome to the Humanist community in Silicon Valley's Sunday Forum. My name is Matt Courtney, and I am a member of the board and a recorder of the Humanist community. The Humanist community is a chapter of the American Humanist Association. Humanism is a reality-based philosophy of life that affirms our ability and responsibility to lead ethical lives of personal fulfillment that aspire to the greater good. We value freedom, health, happiness, fairness, compassion, and using science and reason to acquire and apply knowledge. If these words describe your thinking, we invite you to become a member of the Humanist community if you've not already done so. Membership forms are available on our website at humanists.org. That's humanists plural. If you are listening for the first time, welcome, and we invite you to continue to listening to our weekly forums and other events. You can find all our events listed on the website humanists.org. Please aid us in continuing to present these forums by donating to the Humanist community. You can find out how to donate to our organization, again, on the website humanists.org. So our speaker today is Ron Garret, and he is giving a forum on his continuing series on how we know what we know. This particular forum is on thermodynamics. So Ron, should be able to unmute yourself. Actually,
Hello?
You're unmuted.
Is this thing on?
Yep.
Okay. Let me, what happened to there it is, the share button. Okay, the slides up?
Yes, they are.
Okay. So I actually intended to title this talk Thermodynamics and the Industrial Revolution because those two things are really very intimately related. And actually the story of the Industrial Revolution is really much more interesting than the story of thermodynamics, which is kind of dry and complicated and mathematical. So I will do my best to interleave these two and make the result as interesting as I can. And just realize that these video thumbnails are covering up my notes, so I need to rearrange my screen here just a little bit. How am I going to do this? Okay, that should work. Okay, so this is the 8th and a planned 9 installments of this series. So hang in there, we're nearly done. This particular topic is unique in that it's more complicated than any of the others. There seems to be just an endless warren of rabbit holes and tangents to explore from this topic. It's incredibly rich and complicated and intricate, and it'll become evident in the course of this presentation. This topic is also connected intimately to the topic of the very first talk that I gave in the series about the atomic theory way back in the day. It's unfortunate that this is not quite as interactive as it would be if we were meeting in person, because at this point I would ask if anybody here happened to attend that first talk. But I don't think that's, oh, I see at least one person raising their hand. That talk was given in a different venue, and as far as I know, the video was never published, although I do have a copy of it. So if there's anybody here from ACSJ, or even if HCSV would be interested in publishing it, I have it. It would be nice to get it up on the web somehow. Anyway, so thermodynamics and the atomic theory are intimately linked in much the same way that chemistry and biology are. Thermodynamics just arises from the atomic theory in much the same way that biology arises from chemistry. Biology is what happens when you take chemistry and make things complicated, and thermodynamics is likewise what happens when you start with atoms and make things really complicated by way of a branch of science called statistical mechanics, which was pioneered by Ludwig Boltzmann. So he's an incredibly important figure in this story, and I'm not even going to have time to mention him except to say that there's so much other stuff to talk about that I'm not going to mention him again, at least not today. Anyway, so let's start out by talking about what is thermodynamics. to oversimplify things by quite a lot, it's the study of the relationship between heat and motion. Big spoiler alert, heat is what happens when atoms jiggle around faster. That seems pretty obvious to us today because we live in a world that is absolutely lousy with the consequences of this very simple seeming observation. All of modern technological society is built on it. But it is actually far from obvious that it's true. And it took a few hundred years of concerted effort to really figure it out. And even today, you will occasionally run into thermodynamics denialists in the form of inventors of perpetual motion machines, or advocates of pyramid power or crystal healing or some such nonsense. To get an appreciation for how not obvious it is that heat and motion are connected in any way, you have to go back to pre-industrial times and imagine you are trying to understand the world using just the data available back then. In a world like that, before turbocharged V8 internal combustion engines, before steam engines, before any of that stuff, you had things that moved and you had things that got hot, and not much of an apparent connection between them. In fact, just about the only hint you would have that there's a connection at all is that motion sometimes produces heat, like when you rub two sticks together to make fire. And sometimes heat produces motion, like when you put a souffle in the oven and it rises, or when a tea kettle whistles and produces a plume of steam, and you could imagine putting a pinwheel or something like that in the plume and making it spin. Fun fact, there are no records of either souffles or whistling tea kettles in pre-industrial times, to give you some idea of how far the reach of thermodynamics extends. And did I mention that this topic is a never-ending rabbit hole? Anyway, for most of human history, it was thought that heat was some kind of substance. Aristotle had it as one of his 4 or 5, depending on how you count, elements. The first person known to have gotten it right is Francis Bacon, who in 1600 wrote that heat was motion. The quote is, heat itself, its essence and quiddity, which really means the same thing, is motion and nothing else. Now, this is a really interesting thing for Bacon to say because it's the right answer, but there's absolutely no way he could possibly have known that it was the right answer given the information that was available at the time. The idea that matter was made of atoms would not be even seriously advanced for another 200 years. And the question would not be definitively settled for another 100 years after that. So how did Bacon know? What did he even mean when he wrote these words? Did he mean it literally, or was this a rhetorical flourish? I went to try and find the original source for this quote, and I couldn't find it. The quote itself is all over the internet, but I couldn't find a single citation. So it's possible that this is just an urban legend. I don't know. I wasn't able to get to the bottom of it. If anybody here knows, please tell me at the end of the presentation. I would really love to sort this out. Anyway, so the first baby step towards a real scientific understanding of thermodynamics were made by this fellow, Evangelista Torricelli, who was a student of Galileo's. Torricelli invented the mercury barometer, and that in turn allowed him to measure the pressure of the Earth's atmosphere. And there's a straight line from there to the evening weather report's fixation on high and low pressure systems, because it turns out that water vapor, oh, never mind. Let me just mention in passing that there is a unit of pressure called the torr, which is more or less what it takes to push a column of mercury up by 1 millimeter, and that is named after Torricelli. I'm going to blast through a bunch of names here just to give you some appreciation for just how much effort went into achieving our modern understanding of this topic. That Robert Boyle was an Irish chemist. He's considered to be the father of modern chemistry, who discovered what is today called Boyle's law, which is that a gas at a given temperature has an inverse relationship between pressure and volume. Or to put it another way, that pressure times volume is a constant if the temperature is constant. This is a fact, excuse me, that takes 10 seconds to say, but took Boyle years of diligent experimentation to determine, mainly because he had to invent nearly all the equipment he needed to conduct the experiments. I actually want to stop sharing here for a second and show you a little demonstration. So what I have here is just a plastic syringe, and I'm going to fill it up with some air. And it's going to be a little hard to tell. I'm going to cover up the tip of it here so the air can't get out. And I'm going to push the plunger in. And I'm going to feel some resistance. Then when I let the plunger go, you'll see that it bounces back, but it doesn't actually come back exactly to where it started. Let me do that again. Show you a little close up here. So it's going to, there are actually some gradations here. So I'm going to start it right at the 60 mark. And I'm going to do this experiment again. And you'll see it doesn't bounce back quite to 60. And the reason for that is that there's friction between the plunger and the walls of the syringe. And so to really do the experiment that shows that air is sort of in some sense infinitely springy, you have to invent some more sophisticated experimental apparatus than this. And back in the 1600s, that was a lot of work and it took considerable effort. Let me go back to slides. Okay, so that's Boyle. So, so here's just some pictures of the kinds of equipment that people built back then. This on the right is a water barometer, and atmospheric pressure will push water up to a height of about 30 feet. So those have to be really big. The left is a contemporary for that time picture of a mercury barometer, which is only 30 inches or so, because mercury is much heavier than water. This is a collection of Boyle's writings and some illustrations by him of his experimental apparatus. This is Jacques Charles. I don't actually know how to pronounce it because he's French, so it's probably almost certainly not pronounced Charles, probably Charlet or something like that. He was a Frenchman who discovered what today is called Charles's law, at least by speakers of English, which says that the volume of a gas increases in proportion to its temperature. Then Joseph Louis Gay-Lussac discovered Gay-Lussac's law, which is that the pressure increases proportionately to temperature. And again, all of these things are really easy to say, but took a lot of work to actually figure out and demonstrate that they were true. Benoit Paul-Émile Clapeyron took all of these results and combined them into what is called the combined gas law, which is still one step away from what they teach you in high school chemistry class, which relates all this to the number of atoms or molecules of gas, which is called the ideal gas law. But to talk about that, I would have to tell you about Amadeo Avogadro, and I definitely don't want to go down that rabbit hole because all of this is really a distraction from what I think is the really interesting stuff. And that is that while all of these scientists were off doing science, there was this other little thing going on that today we call the Industrial Revolution. And to segue to that topic, I want to mention another person who made a fundamental discovery, whose name was Benjamin Thompson, but who was and is known as Count Rumsford. Thompson, or Rumsford, or whatever you want to call him, was an American who ended up moving to Germany and got into the cannon making business. And the way you make a cannon is you cast a big block of iron and then you drill a hole into it to make the barrel. And this drilling process generates a lot of heat, which at the time was thought to be the result of releasing a substance, which at the time was called caloric, that was stored in the material being drilled. And the drilling process released this caloric substance and created the heat. But Rumsford showed that you could keep producing heat essentially forever by doing the moral equivalent of rubbing two sticks together. He took one of the tools that was used to bore cannon barrels and intentionally dulled it, and then put it to work on an unfinished cannon that was submerged in water. And after a few hours, the water started to boil, and it would continue to boil as long as the tool was moving, and essentially forever. I couldn't find a record for how long he actually kept it up, but he kept it up long enough to make a convincing demonstration that all this heat could not possibly be the result could not possibly be the result of a substance that's being somehow stored in the material of the cannon that's being machined away. So it must be produced by the boring process itself. Oh, fun fact, did you know that there's a difference between boring and drilling? One of the things I discovered while doing the research for this talk, drilling is making a hole and boring is making an existing hole bigger. But I don't want this talk to get too boring, so let's move on. Except that to move on, we actually have to go backwards again. You may have noticed that Count Rumsford was doing his thing towards the end of the 18th century, the start of the 19th, by which time the Industrial Revolution was already well underway. And the good thing too, there's no way he could have done his experiments. But that's really the story I want to tell you, because that's the process that made the world that we live in today, a world where things move around with machines instead of muscles. And that story starts in 1698 with this fellow, Thomas Savery, who in the aforementioned fateful date of 1698, patented the world's first steam engine. And this is a quote from his patent: "A new invention for raising of water and occasioning motion to all sorts of mill work by the impellent force of fire, which will be of great use and advantage for draining mines, serving towns with water, and for the working of all sorts of mills where they have not the benefit of water nor constant winds." July 2nd, 1698. Quite possibly one of the most impactful dates in human history. That was only 323 years ago, which is a blink of an eye in the grand and glorious scheme of things. And in those 323 years, we have gone from a world where horses were the state of the art in transportation to one with supersonic airplanes and 50% more carbon dioxide in the atmosphere. 323 years, that's all. Anyway, before I dive into the details of Savery's engine, I want to mention this was actually not quite the first steam engine. It was just the first one to be patented and put to a practical use. The earliest known steam engine is actually this little cutie, which goes back to ancient Greece. A fellow named Hero of Alexandria, who lived from 285 to 222 BC. It's not particularly useful, just a curiosity, a parlor trick. And it consists of a boiler connected to a metal sphere mounted on a pivot, and exhaust ports that direct the steam in such a way that when you fire the thing up, the ball spins. And it was just for fun. Fast forward 2,000 years, and we have this, which is Savery's steam engine, the first one that was designed to do something useful. And the useful thing that it did was to pump water out of mines. And I want to go into a little bit of detail about how it works, because it's really kind of interesting. It's a very clever little gadget, and it's notable because it has no moving parts except for a couple of valves. So I don't know, is it possible to see the pointer in the screen share?
Yeah, we've been seeing it the whole time.
Oh, okay, good. All right, so it consists of a boiler that boils some water to make steam. And there's a valve here that you open. And when you open this valve, the steam goes into this chamber, which is full of water, and it pushes the water out. And that water then gets pushed up this pipe here because there's a valve here that prevents it from flowing back down, and another valve here that opens in order to let the water, flow up. And then you close this valve and you spray some water, some cold water onto the outside of this tank, which makes the steam condense. And that creates a vacuum which sucks water up from the source. It closes this valve which prevents the water from flowing back. This valve down here opens up, which allows the water from the mine or wherever you're pumping it from to flow up into the tank and fill it up again. And then you open this valve and the cycle starts again. So this was the start of the Industrial Revolution, but nowhere near the end, of course. Savery's pump worked, but it was horribly inefficient, and it was also dangerous, as the boilers had a tendency to explode under pressure, so there was a lot of room for improvement. The next step in development was this fellow, Thomas Newcomen. who built this steam engine, which was also used to pump water out of mines. Excuse me. Its design might look a little bit familiar to anybody who's ever seen a modern oil derrick. This is a schematic. It's notable in that it is the first steam engine that introduced the use of a cylinder with a piston inside it. But other than that, its operation was very similar to Savary's engine. So there's a boiler down here that makes steam that fills the cylinder and pushes the piston up. And then you close a valve and inject some cold water into the cylinder in order to condense the steam, which creates a vacuum, and then air pressure pushes the piston down. And that is what actually does the work over here on the other side in order to draw water out of the mine or wherever you're pumping the water out of. And there were two big benefits that came about from introducing the cylinder. The first is that the work is now being done not by the steam pressure, but by the atmospheric pressure. So the steam is just there to push the piston up, but that's not actually the force that's pushing the water out of the water source. That's done by the atmospheric pressure, and that's limited to the pressure of the atmosphere, and so you can't have an explosion. And the second is that the water that cools the steam to create the vacuum is injected directly into the cylinder rather than being applied to the outside. And that cools the steam much faster and makes the engine much more efficient. The next innovation was made by this fellow, James Watt, whose name you may have heard bandied about if you've ever paid an electric bill. Watt introduced, among other things, the double action cylinder, where the pressure of the steam pushes the cylinder in both directions rather than relying on atmospheric pressure to push down it, as in the Savary and Newcomen engines. This type of cylinder is what you see on the sides of iconic 19th century steam locomotives, and it's the thing that quite literally drove the Industrial Revolution, and it's the reason that James Watt is famous. So in this cylinder, you have high pressure steam coming in on both sides, and a bunch of valves that are not shown in this diagram that control the introduction of the steam so that the cylinder gets pushed by the steam in both directions, and then is evacuated through this exhaust port here. And that pushes the cylinder back and forth, which is then connected to, in the case of a locomotive, to a wheel in order to drive the locomotive forward. So I also want to mention this guy, John Wilkinson. Not because he invented a new kind of engine, he didn't. What he invented was a new kind of boring tool that was able to produce cylinders that had much tighter mechanical tolerances than were possible before. The Wilkinson boring machine is what made the Watt steam engine possible. That you can only build the Watt style of steam engine if you can make a cylinder with very tight tolerances so that you can get a good seal between the piston and the cylinder walls without creating too much friction. So the story of the Industrial Revolution, and indeed the entire history of humanity for the last 200 years or so, is chock full of this kind of interplay between the development of science and the development of technology. And often the technology leads the science. Better technology makes better tools, and that makes it possible to do better experiments, which improves our knowledge, which improves our technology, and so on, in what we hope is a virtuous cycle. I want to mention just a couple of more players in what is actually the story of literally thousands of people. So in 1858, this guy, Jean-Joseph Etienne Lenoir, built the world's first internal combustion engine. And it looks like this. The basic idea is the same as a steam engine, with a cylinder that uses expanding and contracting gases that expand as a result of heat to move a piston, except that here the fuel burns inside the cylinder rather than outside. And Lenoir even put this engine on a carriage to make the world's first automobile, but he never commercialized it. That honor goes to this guy, Carl Benz, who built the world's first commercially successful automobile powered by an internal combustion engine in 1886. It was a one-cylinder engine that I believe made 2 or 3 horsepower. And the rest, as they say, is history. There is one more person I have to mention, and that is Nicolas Léonard Sadi Carnot. To explain to you what he did would take us deep into the technological weeds. But the short version of the story is that he took all of the science that was available at the time and worked out the math that governs the operation of all engines and any possible engine that turns heat into motion. And he did this by working out something called the Carnot Cycle, which is diagrammed here. I'm not going to go into it. It takes a couple of hours to explain this in an introductory physics class. So, and this is not really about, this is not supposed to be about physics. This is about the history of physics, the history of science. But the upshot is that it's deceptively simple compared to all the work that went into figuring it out. Heat engines work by taking heat from someplace hot and moving it to someplace cold while turning some of that heat into useful work. And the amount of useful work that can be extracted depends on the difference in temperature between the hot source and the cold source. And it's actually the ratio of the temperatures. And this is true whether you're talking about a steam engine or a jet engine. And the absolute best that you can do is something called the Carnot Efficiency. But this is the formula for it. Again, deceptively simple. It depends only on the temperature of the cold region that you have to discharge the heat into and the temperature of the hot region measured in kelvins and measured in absolute degrees above absolute zero. And you can take some extreme cases. If the cold source and the hot source are the same temperature, then this ratio is 1 and the possible efficiency is 0. So you have, in order to have an engine work, you have to start with some kind of temperature difference that you can take advantage of. And this is the reason that perpetual motion is impossible, because as you move heat from the hot source to the cold source, the hot source is going to cool down and the cold source is going to warm up, and eventually they will be the same temperature. And at that point, the theoretical maximum efficiency that you can get out of the thing is 0. And that is just a fundamental law of nature. So if anybody hands you a paper claiming to have discovered how to invent perpetual motion, you don't even have to look at the details to know that it must be wrong. There has to be a mistake in there somewhere. So I was planning to skip over this, but since I'm actually running a little ahead of schedule, I'll go ahead and talk about Maxwell's demon. James Maxwell, who is best known for having worked out the laws of electrodynamics, challenged Carnot, the idea behind this, with the following thought experiment. So suppose you have two chambers that are separated with a little door and a demon that can open and close this door, depending on whether or not he sees a fast atom or a slow atom approaching the door. So when he sees a fast atom over here on what's going to be the cold side, he opens the door so the fast atom comes over here. And when a fast atom over here approaches the door, he closes it so it can't get out. And by opening and closing this door at exactly the right time, he can collect all the fast atoms over here and make it hot, in apparent contradiction to the second law of thermodynamics. And it took a long time to figure out why this didn't work. It turns out that you can show that the work that the demon has to do to open and close the door is more than the work that you can get out of the temperature difference that you can produce. And so if you look at the entire system, it still obeys Carnot's law, the second law of thermodynamics, and you still can't get perpetual motion out of this. There's also this interesting gadget called a fire piston, which is another way of turning motion into heat. It's still in use today. You'll find this sold on Amazon as survival gear. You put a little piece of cotton on the end of this plunger and stick it into this cylinder and smack down on it really hard and compress the air, and it compresses fast enough that it gets hot enough to ignite the cotton, and you can start a fire that way. So there's one last person I want to mention in the history of thermodynamics and the Industrial Revolution, and that's this guy, Randall Dugan Revel. In 1950, I think it was 53 or so, he started to think about the consequences of all of this carbon dioxide that's being released into the atmosphere as a result of burning the fossil fuels to make all of the engines of the Industrial Revolution go. It had been known for a long time that carbon dioxide was a greenhouse gas that trapped heat in the atmosphere, but nobody had ever thought to do the math on exactly how much heat that would trap and what the consequences would be. And Revel did the math, and the result was fairly alarming, and appeared to him that in a fairly short period of time, which he thought would be just a couple of 100 years, that enough heat would be trapped to radically change the climate on Earth. And because of this prediction, he thought it might be a good idea to start actually measuring what the concentration of carbon dioxide in the atmosphere is. As a result of his advocacy, an observatory was set up at the top of Mauna Kea in order to start measuring atmospheric CO2 concentration. And these are the results of those measurements. They started back in the mid-50s when the concentration of CO2 was already well above the pre-industrial levels of 270 parts per million. The measurement started at 315 or so. And they've been going up steadily ever since. And just recently, I read a news story that we hit 420 for the first time ever. The little red jiggles are the seasonal variations that come from the fact that most of Earth's plant life is in the northern hemisphere. And so when it's summer in the so I think it seems like I got this wrong because the concentration is highest in the summer. I think it's because of there's a difference in the distribution of plant life between the two hemispheres. And that results in the seasonal variations as plants take up carbon dioxide and release it again over the course of the year. But you can see that the trend is up. And since measurements have started to be taken in the 50s, the atmospheric CO2 concentration has gone up by about 50%. And the rate of increase is increasing. And this keeps me up at night because the original calculations were that it would take a couple of 100 years for the effects of this to really be noticeable. But if you live in California, you can tell, or pretty much anywhere on the planet nowadays, you can tell that the effects are already being noticed. And these are effects that play themselves out over very long timescales. It took us about 320 years to get from 270 to 420. And unless we figure out some kind of technology to get the carbon dioxide back out of the atmosphere, which is going to be very challenging because that's going to be a very energy intensive process, we're going to be at this level of concentration or higher for a very long time. And that's going to cause very serious problems on timescales that are apparently much shorter than hundreds of years. And we really need to do something about it and treat the situation as more urgent than we have been, or things are going to get very unpleasant. Oops, sorry about that. And that is all I've got. So open it up to Q&A.
All right. Thanks, Ron. If anybody has a question, you can raise your hand using the raise hand feature. It's under reactions button if you're on a Mac or a PC. Dana and Jerry, go ahead.
Yeah, I looked at that seasonal variation on the CO2, and it is correct, because what's important is it is actually going down while the plants are growing. You know, it was peaking in April, which is kind of the beginning of the growing season, and going down as fast as around July. So that graph is okay.
Right. So that's just, it's the phase lag that I forgot as I was looking at it just then.
And it's very interesting, because that basically says the planet is breathing one cycle, 1 year. I'm done.
Yeah. So Ron, do you have any suggestions we should do while we're waiting for other people?
Oh, in terms of what to do about it?
Yeah.
Oh boy. Well, yes and no. My main suggestion is to, I'm not quite sure how to put this. There is a mindset that is sometimes called techno-optimism, which is this idea that there is a long history of predictions of gloom and doom of various sorts. And the track record of these kinds of gloom and doom predictions is very poor. And that humans are very clever and innovative, and they've always been able to come up with something to stave off disaster, despite and make the predictions of gloom and doom not come to pass. And the problem is that this time it's different. And the reason it's different is because this is thermodynamics. And thermodynamics puts hard limits on human cleverness. So for example, we can't build perpetual motion machines. Thermodynamics puts a hard limit on that. And it's not impossible to remove CO2 from the atmosphere, but it's really, really hard. And thermodynamics puts some very hard limits on the amount of cleverness that can potentially be applied to that problem. And so even with infinite cleverness, you can do the math on how much energy it would take to get that CO2 out and the rate at which it could plausibly be done. And so even if you removed all technological constraints and all socioeconomic and political constraints and just applied the physical constraints, it's still a really, really hard problem. And so the first step is to get people to recognize this and take it seriously, and realize that this might be the end of the road for techno-optimism. And we have to really fundamentally change our thinking about some of the kinds of things that are considered good and bad. So for example, right now, everybody is celebrating the end of the pandemic, which it's clearly something to be celebrated. But one of the things that people are celebrating is the resurgence of the travel industry and air travel in particular, which is one of the greatest contributors to CO2 emissions. And one of the things that's going to be most difficult to replace with alternative energy sources, because there is nothing that can compete with jet fuel in terms of energy density. And energy density is really, really important when you're trying to fly. And so we may need to make our peace with the fact that humanity cannot afford cheap air travel because the cost in terms of the externalities of carbon emissions are just too high. And we may need to just figure out some other way to conduct our lives.
Yeah.
And I hate saying this because I love traveling. And we, you know, I feel like a total hypocrite because my wife and I have a bunch of travel booked, you know, planned now. And, and like I said, it keeps me up at night because I really don't know the answer.
Okay. That's a good answer. Now we have a bunch of people with their hands up, so we better start, allowing them to ask their questions. So Herman, you can unmute yourself. There you go.
Okay, thank you. Let me introduce my nephew who's watching with me here. I think you can see us both on the screen.
Hi. Hello.
He's very interested and in fact, maybe a future speaker on climate change. I'm glad that you introduced that as part of the talk that we just heard. But I also wanted to comment that wonderful simple equation that relates the efficiency to the temperature of the hot and cold reservoirs in any engine. It's very illuminating, I think, to keep that in mind. There's another simple equation, I don't remember the exact form of it, which relates the efficiency of an internal combustion automobile engine, or any internal combustion engine, to the compression ratio. Have you ever seen that? Because that's why high compression engines are pursued, because the higher the compression, the greater the efficiency. Of course, the more heat that you give off too by compressing that gas. So it's very interesting to look at these simple equations.
Oh, the whole topic is absolutely fascinating and vastly richer than I was able to convey in this short talk. Thermodynamics touches every aspect of existence. It's just everywhere. You can't get around it. You can, and people do, teach entire university level courses on thermodynamics. And the study of internal combustion engines is one little branch of that that has had a major impact on our lives. I recently started watching a series of YouTube videos on race cars, and I learned some really interesting things about drag racers, top fuel drag racers. They're absolutely fascinating machines. They run in a straight line for a quarter of a mile, which takes about 3 or 4 seconds, because they get up to about 300 miles an hour at the end of that quarter of a mile. Their engines produce 10,000 horsepower, and after every run, which is to say after 4 seconds of running at full power, they have to be torn down and rebuilt because they run so hot that their parts melt during after 4 seconds of normal operations, and they have to be torn down and overhauled after every run.
Wow. Okay. Scott.
I just wanted to point out that there's a proposal to tax carbon. It would be revenue neutral. Everyone in the country would get a check quarterly of their fair share of the revenues generated by the carbon tax. And people who burn more carbon would find, they might have a encouragement not to. That's all.
Yeah, a carbon tax, I think, is a great idea. I'm not sure it's politically viable because you'd have to do it and enforce it planet-wide.
Yes, there would be adjustments for imports and exports. Yes.
Yeah, it's a great idea. It's definitely worth pursuing. I'm not terribly sanguine that it will actually happen, but yeah, if it could be done, that would help a lot.
All right. Dick Hewitson.
Good morning. Your comment about air travel is the one that bothers me every day in this country. I don't understand why people in this country are so anti-high-speed rail. You can, for instance, if I were going to go down to Los Angeles, I could get on a train. It would take 30 seconds to load the train. You go to the airport and you spend an hour just getting onto the airplane. And the electric trains don't cause the problems that the jet fuel does. Do you have any comments on that?
Yeah, that's another topic that somebody could give an entire talk about, I'm sure. The biggest problem with high-speed rail is that for the United States is big, and the planet is big, and there are some places people want to go where it's just not practical. Like if you want to go from here to Japan or from here to Europe.
Well, I understand that, but for instance, between here and Los Angeles, it makes a lot more sense.
Yeah, I mean, I'm all for it personally. They're just all kinds of practical political issues that make it difficult to impossible.
That doesn't happen in other countries.
Yeah, but the places where high-speed rail is most prevalent, the population centers are much closer together. So, even San Francisco to Los Angeles, 300 miles, that's a pretty fair distance. That's about, end to end is probably 2 hours on even a high-speed rail line with very little in between. Now, it's possible that if you built the high-speed rail line that things would grow up in between. But at the moment, the economic challenges are daunting. They're trying to build a high-speed rail line between San Francisco and Los Angeles.
I know.
And it's turning into a disaster.
All right.
I think LA to Vegas is probably the low-lying fruit there. I don't know why they're not doing that.
Yeah. I want to jump in real quick on that because I don't have a whole lot of experience with high-speed rail, but when I lived in Virginia and wanted to visit family in Florida, there was a rail line that was called the Auto Train, where you could actually load your car onto the train and you'd get in a regular passenger car and it'd drive you, and you'd ride from Virginia all the way down to Sanford, Florida. And it was really nice. And stuff like all of the security you have to go through on planes and at the airport, you didn't have to do all that. It was really much more comfortable to get in. You had much more space on the train and everything, but it did take a whole lot longer. It was not a high-speed train. But I could take like everything that could fit in my car, which is quite a lot of stuff. Like I could take that on the trip. And that was great. But still, I think that was probably like diesel electric. So it was very efficient, but still not carbon neutral,
Well, at least when you have rails, you can potentially convert them to electricity much more easily than you can convert automobile infrastructure.
Well, automobiles you can convert to electricity because you can make that.
The difference is that with rail,
them slowly with electric cars.
yeah, the difference is that with rail you can run an overhead cable or a third rail, and so you don't need batteries. With cars, you need batteries, and then you have the battery problem.
Yeah, fair enough.
And you have to recharge them, right?
Yeah. Okay, we can go with Ray. He's got his hand up.
So thanks for your talk. I really enjoyed it and would like to make a couple comments on your lack of optimism for solving climate change. You talked about the need for very high energy density and
For air travel.
for air travel. And in general, if we could get more nuclear energy, that's much higher density than anything we've got with internal combustion.
It's high density with respect to the weight of the fuel, but the fuel by itself is not enough. You need a reactor. And my father is actually here. He was a retired nuclear engineer, so he's could make a more informed assessment of this than I could. But my guess is that designing a nuclear reactor that could power an airplane would be very challenging. Not just in terms of the engineering, but also making sure that it was safe if the plane crashed. That would be a real challenge.
Yeah, I'm not sure that you can put a nuclear reactor on an airplane, but in terms of solving climate change,
Oh yeah, nuclear has got to be part of the solution.
we can eliminate combustion of fossil fuels totally and provide all our energy needs and provide all the energy we need to get the atmospheric CO2 content or greenhouse gas content back down to pre-industrial levels.
Yeah.
And if we do that soon enough while society is still functioning, then we can make it happen. If we wait until society falls apart, it would be much harder.
In retrospect, I would say that the political response to the dangers of nuclear power, that the environmental lobby that chose to respond to that by calling for the elimination of nuclear power, that was a catastrophic mistake.
Absolutely.
And it's one that's ongoing. So I think France, it was either France or Germany, recently decided to eliminate their nuclear program. Which
That was Germany that decided to eliminate it. France went the nuclear route, and they've actually been quite successful in reducing greenhouse gas emissions.
Yeah, I think
they have much less expensive energy than Germany does because of it.
Yeah, the answer is to put research and development into building safer reactors and not building them in tsunami zones. What were they thinking?
Yes, well, much safer reactors are in the pipeline, and they will be online in a matter of a few years.
That's good to hear. That's much faster than I would expect.
Okay.
Within the next 10 years, I think we'll have a lot of new technology nuclear online.
Yeah. Okay, but before we go back to Herman, I do have a quick comment question for Ron. What do you think about, so air travel, we probably can't replace some sort of fossil fuel in the planes themselves. Like you can't put a big battery in a plane. That's probably not going to be viable ever. But what about something where you're creating jet fuel basically by capturing CO2 from the atmosphere and using electricity maybe from a nuclear power plant to create?
Yeah, that's going to have to be the answer. Something like that. Yeah.
Yeah. Okay.
But as far as I know, that technology, it's theoretically possible, but it doesn't. It either doesn't exist or it's not efficient enough to be viable at this point. But yeah, definitely something worth putting R&D effort into. Absolutely.
Yeah, I don't know about directly from the atmosphere CO2, but I think there were some attempts like using not bacteria, but like algae or something, and I know there's like making the biofuel that way, but that would be a biodiesel, right? But I think they were trying to do something similar to make jet fuel. I don't know. I haven't looked at this in a while, so I don't have sources.
Yeah, the devil is always in the details.
Yeah, I don't think that was a particularly efficient way of doing it.
Yeah, so for example, ethanol is actually a net carbon source.
Yeah,
it's actually much less efficient because of all the energy that has to go into processing the corn.
Ray might come back and make a comment on that because I think he's done some research there. But
at least this is what I've heard. I'm not an expert in this.
Yeah, I think you're correct, but I think there is a way of kind of getting around that. But we got to move on. We got a bunch of people with their hands up, so let's go ahead and move on to Herman. Go ahead when you unmute.
Okay, just to comment on the difficulty in putting a nuclear reactor in a plane has to do with cooling the reactor. You need to have a very efficient system to remove the excess heat that reactors generate. This has barely been solved on submarines. It reminds me of the story when I think Hyman Rickover, the father of nuclear submarines, was testifying before Congress. There was a controversy about how you should cool the submarine reactor. The most efficient way to do that is to use liquid sodium. It has very good efficiency in removing heat. But if there was a leak in the submarine, the sodium would kill everybody on board. I mean, it's pretty vicious stuff. And he famously said, when asked whether he preferred seawater or liquid sodium to cool the reactor, he famously said, if the oceans were made of liquid sodium, some damn fool would want to use water to cool the reactor.
Yeah. All right, let's go on to Dana and Jerry. Can I unmute yourself?
Yeah, I wanted to comment that, you know, the underlying assumption that we have the right to travel anywhere in the world anytime we choose for just a frivolous reason. I mean, I really don't think that we have that right for two reasons. First of all, it's harming the atmosphere. And second of all, it spreads horrible diseases all over the world. And those two reasons right there should be enough for most people to say, you know, I don't really need to go to wherever it is this year. I could get by without it.
I want to say something after you respond to that.
I don't know where to have a response.
Okay.
I'm, you know, modulo my own personal hypocrisy on this issue. I agree with the sentiment.
Okay. Well, you know, somebody earlier asked, well, what can we do about climate change? And your answer was you were concerned about techno-optimism, that it was, you know, basically people were too optimistic about technology solving it. And I agree with that. As to the question about what should we do about it, well, that question that kind of needs to be clarified. Are we talking about what should the world do? What should individual countries do? What should corporations do? What should individuals do? And I just want to say that it's a very difficult issue. I believe that James Hansen made a good case in 1988 about how serious this was, and we still haven't responded to the level of what we knew then, and what we know now is much more alarming. I know that there are people who are working on solutions, including various carbon capture and sequestration stuff. All the ones that I've heard about so far are way too expensive and therefore impractical. They're hoping that they'll get better. I'm not too optimistic about that. I think this is an issue that basically, to me, it's the number one priority. And I think everybody should try to understand what it's about. And you can read articles, you can read books, you can take climate science classes. Two websites I can think of offhand that are helpful are drawdown.org, because that gives you some idea of what different technologies can make a difference. And also skeptical science. I think I don't know if it's org or com, because skeptical science is very good about countering a lot of the denial myths. So that's all I got to say for now.
Okay.
Well, why don't you put those sites in the chat?
Okay,
Thanks.
sure.
Yeah. Okay, we'll move on.
Actually, there's an interesting question in the chat that was sent to me privately that I would actually like to respond to, if that's all right.
Go for it.
do you have any thoughts or observations on the recently published UFO videos that seem to defy our current understanding of physics and motion? Yes, they're only UFOs in the sense that they are unidentified and they appear to be flying objects. The one video that gets the most airplay, the most plausible explanation that I've heard is that it is an insect on the lens of the camera. And if you watch the video with that in mind, it seems completely plausible to me. But one of the, again, thermodynamics is how you can know that these things are not what they are, not what they appear to be. So they're saying that these are objects that are moving through the atmosphere at 11,000 miles an hour. That is one of the reports that I read. And that's just not possible because that is more than an order of magnitude faster than the speed of sound. And so something that's moving through the atmosphere at that speed for any sustained period of time is going to generate a lot of heat and is going to make the mother of all sonic booms. And there is just no way that something like that can exist and go unnoticed. So I don't know for sure what the explanation is, but I do know for sure that there is one other than spaceships or secret government programs.
Yeah, I feel like if it was going that fast, it wouldn't look like a black dot. It'd be a bright, shining light from all of the, energy it had to be emitting, or all the heat it'd be creating.
Yep.
Yeah. Okay, got a lot of hands up. Let's go to Jim Naylor. Jim.
Well, I'm going to have to revert to an earlier topic, and that was aircraft fuel. And it seemed to me that the only real resolution of that problem is by burning hydrogen generated by nuclear power through electrolysis of water. And I've read somewhere that hydrogen had the highest density of energy per unit weight. I don't know whether that would have to be in liquid form or what, but I wonder if Ron has any more comment on that.
Yeah, it's true. Hydrogen has the highest, combustion of hydrogen has the highest energy density just because hydrogen is very light. But the problem there is storage. Not only is it's very light, it's also very not dense. And so to get it down into a reasonable volume is very challenging because then you end up with very high pressures. Hydrogen also has a fairly unfortunate history when it applied to aviation. There was this famous aircraft called the Hindenburg. It didn't use hydrogen for fuel, it used it for buoyancy, but that did not end well. So the challenges in handling hydrogen, I think, are going to prove to be showstoppers. There's a reason we don't see hydrogen-powered automobiles, because that's much easier. Any technology that's going to power aircraft, we're going to start out by seeing it powering automobiles. That's where the kinks are going to get worked out. And even hydrogen-powered cars, they haven't figured out how to make those really viable yet.
I saw one the other day parked next to me.
They exist, to be sure, but they're not economical for various reasons.
And there is the problem of hydrogen passing through metals because of its light, small diameter.
Yeah. Storage is
a
real problem.
But there are apparently, I think, metallic sponges that you can store hydrogen in with some sufficiency.
Yep. Now you've got a very heavy fuel tank.
Yeah, I guess. I don't know what the weight to hydrogen would be, a metal of. I had just seen a cursory mention of it.
Now, I have sort of a general rule that applies to life in general. It's kind of the thermodynamics of economics. which is, if it were easy, somebody would have done it already. So if it hasn't been done, it's a good bet that the reason is because it's really hard.
Yeah.
Or impossible.
All right. I want to comment on that. For the hydrogen cars, I think the Toyota Mirai, I think is what it's called, is the hydrogen car. And
Yep.
I've seen them around. There are a lot of them in the area. But to your point, I think the battery powered car has pretty much won, though. We'll see in the future, but right now that's the hot thing coming out. And I don't see a plane ever having a battery, so I don't think that's going to.
Well, even those do exist. There are electric aircraft.
That's true, yeah.
But they have very limited range. They're only a small aircraft, and they have very limited range.
Yeah. Fair enough. Okay, we need to move on. Herman again. I'm doing this in the order that hands come up, so Herman keeps raising his hand, but you should be able to unmute.
Forgot what I was going to say. I'm sorry.
Hi, my name's Rich. As Herman indicated earlier, I'm his nephew and I'm listening in on the first call. Thank you for having this session. I have been studying climate science for several years. And, you know, what we're having is an experience which is not new for humanity. It's unique in that it is a global problem, but what we have is a tragedy of the commons and a situation where the sum of individual selfish decisions are resulting for really disaster for humanity as a whole. I might be interested in putting together a presentation in the future which is focused on individual responsibility. There's a lot of discussion here about potential technologies for, aircraft fuel, for example. But until those solutions exist, the one thing we can do, and I think one of the other commenters mentioned this, is we can control our individual emissions. The sum of human emissions is the sum of individual decisions. And I think there needs to be some acceptance of personal responsibility for this problem. It's much like smoking 50 years ago. Smoking was very common, and then it became understood that smoking was not desirable, and there was a viral acceptance across society, and smoking has declined. We need a similar type of viral acceptance that carbon emissions, especially recreational carbon emissions associated with things like international jet travel, are really immoral. And we're stealing the future from young people and future generations. So I think the answer is in each of us accepting personal responsibility and trying to contribute to a viral acceptance of personal responsibility. That's it. Thank you.
All right. Any comment, Ron?
No, I don't disagree.
Okay. Go to Dick Hewitson.
Thank you. What I wanted to say is a wonderful follow-up from what we just heard. I am not a scientist. I do not know how to solve things scientifically, but I'm a human being, and I'd like to know what I can do to make things right. And I wanted to get back to the subject I brought up before. It seems to me whenever we have discussions, they're always polarized. And when it comes to high-speed rail, in Europe, for instance, it does not replace air travel. It's not either or, it's both and. if I am in Paris and want to go to London, it probably makes much more sense to take high-speed rail. If I'm in Paris and want to go to San Francisco, obviously I'm going to have to take a plane. But anyway, I still feel that in this country, we've got to understand that what high-speed rail is. And it's like the people in this country are deaf to it. And if anybody who has never ridden a high-speed rail train in another part of the world, it's like BART. And I think we all know how efficient BART is. It's BART on a larger scale. It's like getting out at a BART station and getting off in Los Angeles.
I'm not sure I would hold up BART as the poster child for success of mass transit, but I don't disagree with your sentiment. Anyway, Matthew, I see my dad waving his hand, probably because he can't figure out how to do the Zoom hand raise. So can we unmute him? Uri.
What is the name?
Uri.
Uri.
Yeah.
I
The guy waving his.
asked him to unmute so he can go. I can't see everybody on the Zoom meeting, so if people are like waving their hands around, I can't see them.
How about you? Oh, there we go.
I'm unmuted. Two comments. One is on the nuclear propulsion for aircraft. There was a program called ANP, Aircraft Nuclear Propulsion. And the major reason that nuclear propulsion is not suitable for aircraft is that the shielding is much too heavy and much too large. And for that purpose, for the ANP, was developed a special type of reactor with molten salt as fuel. And that is a very efficient reactor, which is now being pursued again for land use. Another comment is on the climate change. Without reducing the population, or at least stabilizing it and reducing the standard of living, there's no solution for climate change. And so far we are ignoring the only possible solution. All of us are ignoring it all the time.
Well, I'm not. I don't have kids.
Okay.
I see Moshe, actually, Ilana Svantov waving her hand. And she's not muted, but I still can't hear her. Maybe she is muted. Yeah. Ilana, you have to unmute yourself.
Yeah, I clicked ask to unmute, so she should be able to unmute.
I don't think she can hear us.
Oh,
there you are.
Okay. Well, nobody mentions our wonderful exponentially developing technology, and we are on Zoom instead of driving to some place that is where we used to meet in groups and have to drive there. So now we are meeting on Zoom and hearing a wonderful presentation and discussion. And in the modern world, as it goes forward, there is virtual reality. And maybe Ron is even too old to be using virtual reality, but the kids sure use it to experience as if they are there. So a lot of the travel for tourism, I will say, will be possible with virtual reality, which will save traveling by airlines. And a lot of work from home is being conducted now, and a lot of people, companies discover that people are more efficient working at home. So this will save a lot of travel by car to work. So I think that the technology that we are developing may solve a lot of the problem, may reduce a lot of the additional carbon that we are putting in the air. And on top of that, we need to eat no meat and no chicken And that will help a lot for our hot gases that will reduce the heat in the atmosphere. Anyway, this is just my contribution for the technology that I think is growing at an exponential pace. Thank you.
Just because most people here probably don't know this, but Ilana lives in Tennessee, and so does Uri, who is my father. So we definitely have people attending who would not normally be able to, but for this technology.
That's nice, but I have to say, meeting in person and having all the food that we have for the lunch and everything is, I definitely miss that as well.
Yep.
But we will try to continue to post these online for people who can't actually show up in person. Ray Sunby.
Okay, it's been a while, and I've got comments on a lot of the other comments that were made. Hydrogen energy density, I did some study on this, and the only place where hydrogen has the highest energy density is in the realm of nuclear reactions. So as a fuel for an automobile or a plane, it is not the highest energy density. Greenhouse gas sequestration.
Sorry, what does, relative to its mass?
Relative to its mass, I believe, yes.
Because it's true, that certainly would be true relative to its volume, but relative to its mass, that would surprise me. Do you know what does have the highest density?
Mass in nuclear reactions.
Oh, no, I'm
higher
talking about
energy
just
density than uranium or
Oh, yeah, clearly.
or any of the others.
I'm talking about oxidizing fuels, chemical fuels.
Yeah, there, I don't think it is the highest energy density based on the research I did.
Do you know what is?
I read that, but I don't remember.
Okay.
Greenhouse gas sequestration. The biggest method of sequestering greenhouse gases is our oceans. Has been throughout history, and I think can be again if we can restore the health of our oceans. We can do kelp farming, we can do pH balancing if we have enough energy to do it cleanly and so on. So I think greenhouse gas sequestrations, the oceans have to be a big part of the solution. On population, there's a correlation between the number of offspring people have and the wealth of the area they live in. Higher wealth leads to lower population growth. And again, with enough energy, we can increase the wealth of the Earth's population and therefore decrease population growth with that method. Personal responsibility. I think that what needs to happen is we need to come up with something that will solve the problem, not just make steps in the right direction. If everybody was willing to go back to the Stone Age and live that kind of a lifestyle, that wouldn't solve climate change. There is already too much greenhouse gas in the atmosphere that won't decay away before we have serious lack of livability of our planet. So we need a plan that will solve the problem. Yeah, I think that's probably what I want to say. Yeah, oh, one other thing in terms of personal responsibility, what I have done is I've thought about what can I do to best help the situation. And I can, recycle my plastic drink bottles, and I can drive less or any of these other things. They're not going to make any noticeable difference. Even if everybody did that, we can't solve climate change. So what I've done is I've studied the situation, and I've studied nuclear energy, and I know that that has enough energy to solve the problem totally. And so I've become an advocate for nuclear energy. And if more people did that, if they educated themselves, there's a book called Unintended Consequences. It's free online. It explains the whole situation, why solar and wind, while they may be part of the short-term solution, long-term, it's not a sustainable solution. So if people can educate themselves and then become an advocate for what can be a total solution, I think the more people that do that, the better off we'll be.
All right. Any comment, Ron, before I move on? Okay.
Nope.
Dana and Jerry.
Did you have something to say? Yeah, well, one thing about crossing oceans, I just wanted to point out that Greta Thunberg took a sailboat to go from Europe to the United States. She didn't want to do air travel. On this whole issue of climate change, we're getting into a lot of details here, and we're getting to some high-level stuff. But to me, what it comes down to is a very complicated issue, and there is no guarantee that there's a good answer. About the only thing that I can say for certainty is that every day we continue on the current course, the end result is going to be worse. And so people have, you know, somehow we have to wake up and face reality here. On the personal responsibility, I think the more personal responsibility, the better. On the other hand, there's a limit to, you know, to what you can do with personal responsibility. And it could be that you need systemic change. I'm pretty sure you're going to need systemic changes to do what's needed, if even what's needed is possible. I just will advocate that people learn as much as they can about this issue because it's number one. I'm done.
All right. Still no comments, Ron?
No, I'm just echoing my own thoughts mostly.
Okay, we'll move on to Randy. Should be able to unmute Randy. There you go.
Oh, hi. Can you hear me?
So did you say we had a hard cutoff at 12:30?
Yeah, we'll do, this is the last regular, well, I'll stop the recording after this question.
Okay, I'll try and be brief. Granted, there are a lot of people that have great intentions, great knowledge, great learning, but I was a little dismayed by Ron's answer about the UFOs. You know, science has been full of conventional wisdom, and to just completely dismiss curiosity about potential and not even to think about pursuing or thinking about other alternatives just surprised me. Thank you.
So let me phrase my position on that in perhaps slightly less loaded terms. I'm not incurious about these things. I would very much like to know what they are. That, you know, it's kind of fascinating that they haven't been able to figure it out. But there are only two possibilities. It will either turn out to be something fairly mundane, like an insect on the camera lens, or it will turn out to be something that upends my current understanding of the laws of physics.
Yes.
And if I have to put money on it one way or the other, based on what I know right now, I'll give you long odds against my current understanding of the laws of physics being upended to that extent in my lifetime. So it's just a probability assessment on my part.
Yeah.
Yeah,
Well,
it's possible. It's possible that it's aliens. It's possible that it's some advanced technology. I'll give you long odds against.
Well, thank you. I understand, and I probably agree with your assessment of odds, but you know, intellectual curiosity over the years has shown that our understanding is wrong about many things. Thank you.
That's not quite true. I mean, yes, science continually revises and refines its knowledge, but it's extremely rare for there to be radical changes in scientific understanding. In fact, in the entire history of science, it's happened twice. Once with relativity, and when relativity displaced Newtonian mechanics, and once when quantum mechanics displaced classical mechanics.
Yeah.
So in 400 years, it's happened twice. And that's the main reason why I give long odds against it happening again in my lifetime.
Okay.
And certainly, if it does happen, it's extremely unlikely that the source of the data that will cause that upheaval will be something as mundane and popularly sensational as UFO videos. You know, the odds against that are just, to me, indistinguishable from zero.